So today I'm going to about AstroSat, of course, and I'll try to keep this in a level where I'll keep the technical details will be lower. So I will not describe to you what AstroSat is. I'll just tell you a few brief things about AstroSat. First of all, that it was launched about 6.5 years ago, and it has about 5 instruments, and it has, what I wanted to emphasize is that it has a lot of advantages. And one of the advantages of having 5 different instruments, it is incidentally, it's a multi-wavelength thing. That is, you have X-rays and a UV telescope there. So it has a lot of advantages, and one of the advantages is that it's one of the satellites which has done studied a whole host of subjects in astronomy. This includes galaxies far, far away, high redshift galaxies. It includes things that I'm talking about, black holes and neutron stars today. It includes looking at stars in the clusters of galaxies. In fact, it has also studied one of our closest stars, Proxima Centauri. And so the range of subjects which has done has been very wide. That's because of its multi-wavelength nature. We had a couple of great, good results coming out of it. For example, detection of UV emission from distant galaxies, and the measurement of polarization from one neutron star system, neutron star Crab Nebula, which is there, and these were reported in Nature reporting on it. And overall, the advantage is that it has produced more than 200 publications, about 15-20 PhD programs, and that would be some kind of measure of success. However, I'd like to emphasize one more important success it has, which is less emphasized, is that out of all the users of AstroSat, nearly half of them are from different parts of India. In particular, half of them are from Indian universities who would not have had access to doing astronomy in general. And for example, I can tell you that about a few months ago, there was a publication in monthly notices, MNRS letters, which, as you may know, is one of astronomy's prestigious letters, one publication. And that publication was about AstroSat observation of a neutron star. There was that the first author of this paper was a PhD student from Misra. And this was the first astronomy paper from Misra ever in things. So this kind of advantage was there, given AstroSat things. So AstroSat has many advantages. And in this particular talk, I will talk about only a very small subsection, especially on what AstroSat has done on black hole systems. And even that, there are 2 kinds of black hole systems, one which are in hosts of centers of galaxies. They are massive black hole systems. One are the smaller 10 solar mass black hole systems. I'm going to talk about the ones which are the smaller ones which are in X-ray binaries, what do we call? Only one subsection of the black hole systems. And even then, I'm going to talk only about a small fraction of what AstroSat has done because of the wide topic in there, and I just want to make sure that I have a coherent talk. Also the fact that I'm going to talk more about what I have been working on, because I've been lazy to look up and make a full review in the whole thing. That is not one of my things which I want to do out there. So just to keep you in mind, we're going to talk about something which is very specific, and while AstroSat has done a large number of things elsewhere. The very specific thing we're going to do is this kind of a painting which I keep showing. This is what is called an X-ray binary system, that you have a black hole sitting right in the center out here. This is a regular star going around the black hole. And when the star and the black hole are close to each other, matter can flow from this star towards the black hole. And because the star is going around the black hole, it has angular momentum, so it doesn't fall directly to the black hole. It forms a ring around the black hole first. And if nothing else was there, matter would just go around in a ring. But there is turbulence in this gas, and that's a whole topic by itself. But because of this turbulence, and it induces viscosity, this gas starts to spread out, and in some ways forms a disk. like structure. Viscosity has another thing, that it heats up because viscosity like friction, and because of the viscosity, this disk gets hot, and as it gets hot, it produces radiation. This is the story we have been told, right? This is the kind of, but one thing which you may look from this, that this is a painting. It's a drawing of all things. What we really know is something like this. What we really know is that there's something like a disk which comes in, at least we think, and it terminates at one point. I'll tell you why we think it terminates. And some region forms here, maybe, and which is like a hot disk. So I'll try to explain certain terminologies here as we go along. The first confusing terminology, if any of you are not familiar with X-ray astronomy, is this thing which we can never get out of. We use the word hard and soft. Now, hard X-rays means high energy X-rays, and soft X-rays means low energy X-rays. And it has got into a system so much that no matter how much I try, I keep saying hard and soft all the time in the thing. So, and this terminology of hot disk and cold disk. We are talking about X-rays. So, the definition of cold disk is something which is 1,000,000 degrees, and while the definition of a hot disk is something like 100,000,000 degrees. So, when I use the word cold disk, I mean something which is just a paltry 1,000,000 degrees level. And when I use the word hot disk, I mean something which is hundreds of millions of degrees temperature. So this is the kind of general, and I'll try to motivate why we have this kind of a general picture in this thing. But before I go there, this solution, this structural idea of a cold disk was done in 1973 by this amazing paper which came out in 1973 by Shakur and Sunev. I don't really usually mention citations, but someone told me that this is the most cited astronomy paper ever. So if anybody else knows otherwise, its present citation 9,000. I mean, a citation about a year or two ago was 9,000 citations. The other interesting fact for all of the young students here is this paper has nearly 10,000 citations. It has 18 pages of long paper. It's a phenomenal long paper. But the citation and the whole theory which people talk about is given only in 3 pages. So the rest of the 15 pages have been missed out in the whole thing. But it has a lot of wealth of information in the work, and people did. The amazing thing was, this theory tells you how a disk should form around a black hole and all those things, but it was Newtonian. I mean, in some phases it was semi-classical, it was Newtonian kind of thing. And 1974, within an year of this theory coming out, was a full general relativistic theory by these two famous people, Novikov and Thorne. They sat down in 1 year and made this complete calculation for the accretion disk theory. So this kind of accretion disk theory is now known for more than 42, 43 years, well established and all. And again, as I said, this is 107 pages of wealth of information which one should look at and read it, and that's how you make subliminal papers of that kind. There's a vast difference in citation, and I want to bring that into account. That the vast difference in citation is because what Novikov and Thorne did in 1974 quickly was to do a full general relativistic theory, but at that time there was no way to test it. There was nothing to differentiate these two things out here. And one of the main things I'm going to try to do is that AstroSat has now given us a chance to go from here to there and to make the predictions. So that's one of the reasons why I brought this up. But let's get back to our and that is just this simple picture of a cold disk and hot disk and jet. Why do we think it is like this? Because when you look at a black hole systems today and you look at a black hole system after a month or two, it looks different. And what it looks like is, without going into it, you look at this blue curve, this is spectrum of a black hole system. Sometimes the total energy coming out seems to be coming out at around 100 keV. And sometimes it's coming out, like when you observe it some other time, it looks like this red curve, and it's coming out into lower energy. This part is getting absorbed because of absorption, so, but peak is around in low energy, and sometimes it is high. These two things are called generically hard and soft states of the thing. And the way we understand this is that if you have a structure like this, and you have a cold disk which will produce cold or low energy soft photons. If this dominates, that means if the truncation radius is close to a black hole, then you will get something like a soft spectrum or this red light spectrum. And if this hot disk dominates, then you come into that part of spectrum. Now, just to get into the radiative process, a little bit of the physics part of it, is that in the cold disk, the assumption here, or the self-consistent assumption here, is that the emission is coming out as a black body emission. And this is all a black body emission. It has a range of temperatures here. Each region is giving out a black body region, and that is why we are seeing this. While this hot disk, we have strong reasons to believe, comes from a process called comptonization. And what happens in thermal comptonization is that you have hot electrons, which have not in a, they have hot electrons here in a dilute form. So when the low energy X-ray photons or soft X-ray photons enter this, they scatter over the hot electrons, and this process is called comptonization. They gain energy, and that is how these low energy photons coming from the disk become high energy ones out here. Right? So that is a generic model. Again, to repeat, this is a generic kind of a picture we have. There is a cold disk and a hot disk. The cold disk gives low energy soft X-ray photons. The hot disk gives high energy photons, and the process by which this high energy photons is something called thermal comptonization. That is when low energy photons scatter off electrons and produce. Sure. No, right? They may produce synchrotron, but in this kind of system, the dominant mechanism is the comptonization, thermal comptonization.
Okay, it is not possible to detect.
No. If you estimate how much synchrotron will be coming from here, it will be very low. This process will be the thermal comptonization process.
So you're saying that the dominant process here, because you would imagine that it also in the hot disk also you have black body.
No, the hot disk is too dilute. So absorption doesn't happen, so it doesn't reach thermal. The photons don't reach thermal equilibrium. So because they don't reach thermal equilibrium, they don't emit as a black body.
So it's too dilute.
It's too dilute. So for anything to be a black body, you need to have absorption and thing matching. So that doesn't match up. It doesn't come. So it's thermal in the sense of the electrons are in thermal, they're thermalized. The photons have not thermalized. So that is it's called sometimes called unsaturated thermal comptonization. Unsaturated means non-comptonization.
So why is it that both processes don't happen at the same time?
I mean, this case is happening at the same time. I mean, there are two regions, and we see this thing, but it's a domination. Whichever one dominates, we see a spectrum. In fact, we see sometimes spectrum in betweens, intermediate states also seen. So this is it. And don't take it to me. There are many other things which say that there should be a corona on top of here, different geometric shapes. But this is a generic idea which we can follow up on this, right? So this is the so far story before AstroSat, and then came AstroSat. But before I come to AstroSat, sorry. Let me explain what you can do with such kind of thing. These photons, when you have a photons coming here, they will thermal comptonize, and instead of plotting this regular shape here, I'm just plotting you a real theoretical curve, or this is the kind of curve which you will see. Now suppose what happens is, suppose you increase for a moment the cold energy photons. Like, for example, this is the kind of photon, and this is the kind of spectrum we can see from AstroSat. So we can now measure this kind of complexity and compare. The difference with what AstroSat can do and another thing is that because we have two instruments, one low energy and one high energy, and this is observing the source at the same, we can see a very broad band of energy band, all over the place, right? So then we can constrain the spectrum much better here than in the censored board. This could have been done earlier by other satellites, but AstroSat also provides you information on the time variability of the source. So for example, this particular data is for a source by black hole so-called 661. You see this object line move. These are not error bars. This is actually the source is going up and down like this. And but this is stochastic variability. When we look at something like this, we cannot make sense of it in the whole thing. So what we do whenever we see something which is variable, we employ a mathematical tool called Fourier Transform. So we will Fourier transform this observed intensity versus time, and once we Fourier transform, we square it, and we get something called a power spectrum. Now the power spectrum tells you, if you see a system like this, what is this variability about? Is it varying in 1 second? Is it varying in 0.1 second? Varying in 10 seconds? Or is it varying in? And this is what a power spectrum tells you, that suppose I take a power spectrum and look at it. For one example, it tells me that around 0.3 hertz, which is around 3 seconds, there is a lot of variability. And also there is a lot of variability around 3 hertz, which means 0.3 seconds variability. So these systems are varying in a, and the system changes. It has different kinds of variability. The key advantage of AstroSat here is that you are getting the timing variability information and the broadband spectral information for the same observation source, and that has been the key part.
Other detectors also can detect this, right?
Other telescope can either do a timing.
In a short time scale, the variability, earlier it has been detected.
Okay. So, for example, the most important variability study was an instrument satellite called RXT. Now, RXT has observed these variabilities. It has, in fact, generated these kind of power spectrums. But the limitation was that its energy range was much smaller. It was only from 3 to 10 or 20 kb. Now we have a much wider range, so we can constrain the spectrum at the same time as we are looking at the variability. Constantly changing. We cannot compare the spectrum at one time and the time variability at some time. We do it at the same time, so that makes the advantage there in the whole cell. Right. Now there's one more thing we can do. Because we are looking at this different energy ranges, we can find things like the fractional RMS percentage. That is, if I go here and say, okay, at 0.1, what is the variability? 0.1 hertz, let's say 10 seconds. What is the variability? Then I can say, how does this variability change with the energy of the photons? And that is something which we can do in a very precise and beautiful way. That this is a fractional RMS, that is how much variability is there at a given frequency, let's say 0.1 hertz, or that is 10 seconds, as a function of energy. So in this case, for example, it tells you that the fractional variability is going down with energy in the thing. More interestingly, we can also measure the time difference between photons coming at a higher energy, high energy, and compared to low energy. So if we consider the time difference between photons coming at 4 kV compared to others, we can measure this. For example, at 16 seconds, we can see that there is some variation in milliseconds, and I'll show you better ones later, where you can now measure the time difference between the two photons energy. So given this wealth of information, we have to construct some kind of a model and some kind of interpretation to say what does this all mean and what does this tell us about the system that we did not know beforehand. And like I was saying, we can do this for different frequency ranges, so the wealth of information is very large. So let's get back to our picture of, yes, please. No. I'll come to quasi-predict oscillation later. Those are not quasi-predict oscillations. I'll come to quasi-predict oscillations. Let's get back to our general picture that you have a cold disk, hot disk, thermal combinations producing this theoretical curve out here. Now, we want the system to vary, so what can we vary? We can vary let's say the cold disk temperature, suppose it varies here. What is the expected variation we should see in the spectrum? So if I calculate it theoretically, you can do it in a self-consistent way, and you're saying that the energy output from this hot disk will remain the same. So what happens is, if I increase the cold disk photons, the low energy photons will go up, but high energy photons will go down. Now why will it go down? Because once I increase the low energy photons, it will cool that hot disk down. The temperature of the hot disk will go down, because if the energy output of the hot disk is the constant, and what is the energy output? That is all the enhancement it is doing to the low energy photons. If you increase the number of low energy photons, then it has to do less enhancement, but it has a fixed energy budget. So the only way it can do that is by decreasing its temperature. So the temperature falls like this, and you further increase the thing, the temperature will fall. So it's good to look at it in this way, that you start off with a system like this. As you increase the temperature here, the low energy photons will obviously go up, but high energy photons will come down, like that. So from here you can calculate that if you look at a fractional RMS, how much variation would be there as a function of energy, the fractional RMS will actually go down as things. Because here what we are doing is, you can see that the variability decreases as if it is induced by variation in the cold disk temperature out here, right? But that may not be the only reason why the system is varying. The system could vary because this hot disk is varying. Let's say the energy input into this hot disk is changing, so the temperature here is varying out there. That would mean that the low energy photons don't change, but the high energy photons will keep going up. So you will get a system like this, that you start off with the red line. As you increase the temperature here, it will keep going up and down. In that case, your fractional RMS changes, will increase with energy. So this fractional RMS versus energy is a way to discern between what are the different processes by which things are varying in the system. Of course, things are more complicated always, and we know that. Both these things can happen at the same time, that there could be variations in the cold disk and in the hot disk. And what we know is, if there is a change in the input photons, the RMS will go down. If you change in the heating rate, RMS will go up. And if you combine them, you can get different kind of shapes of the curve of how the fractional RMS changes with energy. And also, if there's a variation here, and after some time there's a variation in the hot disk, there's a time lag between the two, then this would induce a time lag between the high energy photons and the low energy photons. And this is exactly what we have measured from AstroSat in the whole. So what we can do is, we can take all these observations of RMS and time lags and energy, and I'll just quickly go through this part, that you can now look at what part is varying in which one. Like for example, you can find out that like if the temperature of the electron, how does it vary with the variability in the frequency? So I can now quantify, I mean, this is for different kinds of black hole systems. One is Cygnus X1 in 2 different times, and 3 black hole systems. Not going into details of this, but I just want you to get the message that now we are in a position, by looking at all this data, to say this variability has been induced by variations in this temperature incoherently with variations in the other temperatures. So this gives us an insight into how the systems are varying, and not only that, we can get to know how the time lag happens. What is the difference in time lag between the, let me go back to my image here. I can also estimate what is the time lag between the variation here and this hot one. And this gives me a quantitative measure of what's happening in the picture. And that I would now have to feed it into my more generic accretion disk theories to see what is the reality there. Yes?
So the delta T, how are you getting that? Is like you're fitting a Compton model and then calculating?
Yes. T is calculated by, you find, sorry, so let me get back here. You find, you vary both hot and cold disk photons. This gives you a predicted fractional RMS versus energy. Because you also induce a time delay between these two, it gives you a prediction of how the time lag changes with energy. These are data we have. We can fit the model and get the parameter of what is the temperature variation and what is the electron variation. Right? Okay. this seems to be a matter of detail. I started this off because I thought I'll show you what is the. There is something and much more important. And
Typically, what is size of the hot corona?
around 1020 RG, which for Cygnus X1 would be around 50-100 kilometers. So these are not light travel times. The time travel distance between these things are much longer than light travel times. So it doesn't affect it. There is something amazing which X-ray binaries give, and it is personified by this picture. Sometimes when you do a power spectrum of a system, instead of showing you broadband noise and wind, it shows you coherent features which are called quasi-periodic oscillation. If the variation was exactly sinusoidal, this would be a delta function, straight. Because it's not a delta function and it is slightly broad, it is called periodic. So there is a variability in a particular frequency, but it is not exactly sinusoidal in a way. There's a huge amount of theory on understanding what is quasi-periodic oscillations are, but we observe quasi-periodic oscillation. This we have been doing for the last 30, 40 years. Why is this so interesting, important? Is this idea that the systems are giving out this quasi-periodic oscillation characteristic gives us a handle to understand general relativity and understand the system. Even though we may not know, for example, why the system is oscillating, what is the reason for this system to oscillate, we can identify what is the characteristic frequencies of the system and try to adapt to that one. Again, if you look back at this picture, there is a truncation radius here. There is a radius here. Now, in general relativity or in any system like this, the frequency or the time scale of the system will constantly change. For example, let's take the time scale for all these matters going around the black hole. So there is something called a Keplerian frequency. That is the time taken for a particle to go around the black hole. That will change as you go. So there is a whole host of frequencies in the system. But one particular frequency is being picked up, and we are seeing this oscillation out here. It's natural to assume that this frequency is something to do with this truncation radius, because that truncation radius will give us a characteristic frequency, which will be done. Again, I'm telling you, we are not looking at, we don't even know how the system is doing. For example, we are not saying that we know that whether this ball is going up and down like that. What are the dynamics? People have tried very hard and not found any good answer for this question. But even though we are filled with ignorance, we should be able to identify the characteristic system of the system. And let us talk about what are the characteristic system at a given radius. In Newtonian physics, for a particle dynamics, it took me, I mean, it's very interesting to know, is that there is only one characteristic frequency, which is the Keplerian frequency. That is the frequency in which a particle will go round and up. In Einstein's general relativity, this has changed. The first other appearance which comes in is called the epicyclic frequency. The epicyclic frequency is if you take a particle, circular particle of a particle going around, and you perturb it in the radial direction. In Newtonian thing, what will happen is it forms an ellipse. Now, the reason it forms an ellipse is because this radial frequency perturbation is identical to the Keplerian one. So, in other words, the epicyclic frequency is equal to the Keplerian frequency in radial, and therefore you form an ellipse. In GR, and this property is only for 1 over r square forces. Since GR is not a 1 over r square force, there is a difference. The epicyclic frequency is different than the Keplerian frequency. And it decreases. And in the as you go closer to the black hole, the epicyclic frequency is lower and lower than the Keplerian frequency. So that instead of having 1, it has split 2. Third frequency, and this happens only if your black hole is spinning, that if you take an orbit and you push it upward in the height, instead of pushing in the radial, you put it up in the height. If the black hole is not spinning, there is no special direction, so it will not vary at all. But if a black hole is spinning, it affects the space-time such that when you push it up, it will oscillate. And that oscillation is called the lens tearing frequency. And so these two frequencies are completely from general relativity in the whole thing. So the idea is, if we can identify one of these QPOs, any of these frequencies, we would be in a position to say that we are doing what is named general relativity. Yeah.
So these frequencies, there are three frequencies, but they're all functions of R.
Yes.
So still you pick one of them.
Yes.
So
and
accumulation of matter somewhere.
no, the hypothesis is that this truncation radius could be the character, because there is no other radius here which seems to be characteristic.
Yes.
So see, if I did not know anything about black holes, I would think that they should oscillate in all frequencies.
Yes.
Now I'm observing them to be oscillating in only one particular frequency. So that by chance means that there is a one characteristic radius which is important, and by that I would like to associate it with the radius at which we truncate the disk, because this is required for the spectral fitting, which is independent thing in the whole thing.
Have both the soft and hard component detected.
Hmm.
At what level can one narrow down the location of the truncation radius of
The next slide of my talk. That is what I'm going to talk about, and that is the advantage.
This epicyclic thing, so we know frame dragging, right? Frame dragging is
Frame dragging is the lens tearing one.
lens tearing. So what is it that the epicyclic thing does?
Oh, epicyclic thing does this, that you know that in GR there's something called a last stable orbit, beyond which the matter doesn't flow through. What does it mean? That if I have a particle there, if I perturb it, it goes off, which actually means the epicyclic frequency is 0. That is, it is negative. So epicyclic frequency is same as the Keplernian frequency outside, and goes down, and because it becomes 0 at the last stable orbit, that orbit is defined as last orbit because it becomes unstable. See, any frequency becoming imaginary would be
You're referring to the radius.
radial one, and while the lens tearing one is the vertical direction. This has been being gone on for a long time, but often, not everybody, but some people missed out that these are not the only characteristic frequencies of the system. Yes, Mercury's position. The Mercury position is the epicyclic frequency. That is that's how we know that GR was confirmed from that one, because the epicyclic frequency. That is the thing. You can in fact have combinations of these frequencies. That would be the frequency, which is also possible, and people have tried that. But the main thing is people also know that this is not the only characteristic frequency of the system. There are two more characteristics of frequency of the system, and those are the disk itself. One is what we call the sound crossing time. That is, if you go back to this region, there's a temperature here, out here. There's a speed, sound speed. So you can calculate the time taken for any sound wave to go from here to there. And since this sound speed is much smaller than what is inside here, is dominated by the sound speed here. So one characteristic frequencies is the sound crossing time, R by CS. The other is the viscous time scale. That means the actual matter flow from the truncation radius towards the black hole. How long it takes that. These two are not frequency, they're based on particle information. These are based on hydrodynamic equations, solutions. So there are 5 of them in the thing. And the difference is these 3 are just dependent on the radius, while these 2 depend on the hydrodynamic flow. In other words, they also depend on how much matter is flowing in, or what is the accretion rate of the system, right? Now, what gave a phenomenal advantage that at the same time we are looking at the QPO, we are no confusion that the QPO is there. We can measure the spectrum from the larger band. This allows us, because we can measure the spectrum, we can measure the truncation radius and the accretion rate at the same time. And there's a lot of complications here. We have to use the full general Novikov-Thorne's equations for the spectrum to fit this kind of thing. But in general, you can fit it, and you can find from fitting the spectrum, because you have a wide range, the radius and accretion rate. So in summary, now you can do something which is spectacular. You can find the radius, accretion rate, and at the same time, you can measure the characteristic QP frequencies. So this is what we found for one black hole system. We did it. We found the QP frequency versus transition radius, and there's a general trend of it going down, which is correct. You see, because as the radius increases, frequency should go down. This is radius of truncation radius. Truncation radius in Schwarzschild radius, terms of RG. Sorry, it's not coming up in terms of Schwarzschild radius. QPO frequency going down. And if you plot the QPO frequency with the accretion rate, which you can now measure, there seems to be a lot of scatter in this whole plot. However, you can do an interesting thing, which is, well, you take the QPO frequency divided by m dot, and then plot it against radius, you find this nice curve out here. There's a correlation. And the amazing thing is, this is exactly the correlation predicted by Novikov and Thorne when you do generalistic this theory, that if you calculate the dynamic frequency, which is r by Cs, r by the sound speed at that radius, they found that it should depend on m dot, so only proportional m dot. So if you divide that, this function becomes a function of radius only. And you have this important definition of r by rg to minus 2.5, but these a, b, d, e, l are functions of radius and the spin of the black hole. These are the generalistic corrections. If you didn't have a, b, d, e, l, this is what you would have got from Newtonian work. The way Novikov and Thorne put it, that given Newtonian solutions and put the exact GR corrections to these curves out here. And this curve which we find, which is actually fitted in the black one, is the prediction of Novikov and Thorne. So what we can do is, because we now know the radius and m dot, we can now fit, or I can show that this seems to be going well with the black hole system of, okay? But we can do better, and we are better because there was another satellite which went up inside HMXT. This is a Chinese satellite which was sent up 1.5 years after AstroSat, and the inside HMXT has the same kind of capabilities as AstroSat has. It has differences which I will not go into, but it can also measure the spectrum very well over broadband. It can also measure variability and find quasi-periodic oscillations. So like this, they can also measure the QPO out here, much less version than AstroSat can, and they can also measure the spectrum in a broadband. So they did the same analysis. They found that the QPO frequency increases with RN, which is completely opposite to what one would expect. They found the QPO frequency increasing with m dot and all, but when they put these are the black dots, these are the red ones are coming from AstroSat, and when they put the QPO frequency divided by m dot as r, it matches with roughly matches with the Novikov and Thorne theory. So this gives us confidence that things are going good. And now we are doing further progress, that we are looking at more AstroSat observations of our sources, and we can now span more areas of mass and radius. This blue region is what I was showing you before. Now these are preliminary results which we know. We can scan different areas of mass and radius out here from different points, and we can play this game again. And what we find is, this is the original curve, and somewhere in the curve which are falling in like this. But these are preliminary results. We are looking at it but this gives us a scope to now extend the work to different kind of black hole systems, larger areas, larger range, to verify whether this is correct or not in the whole thing. Yeah, so I better get ahead. So now I have told you things about what we did, what we know. But that is not at all, in my opinion, the important thing which AstroSat has done. Any good observatory or anything should give you more questions than answers. And now I'll go into what are the questions which AstroSat answers. And before that, let me go into AstroSat has given us something called puzzles. And let me define what puzzles are before you. See, whenever you land up with a problem in astrophysics, you can't answer a question. Suppose you cannot answer a question in astrophysics. You can ask the question, what is the reason for it? I mean, you have to have an excuse, right? Why are you not able to answer the question? The standard is, why are you not able to answer the question? The standard reason is you have insufficient data. If you had much better, higher data, you would have answered that particular question. There could be another reason, which is permanent in astrophysics, is nothing to do with data. It is the fact that you don't the underlying physics is not understood. Like if you take, for example, the solar cycle or many of these things about turbulence and accretion disk, we don't understand the underlying physics, so we cannot answer this question. In fact, much of our science strategies is we take questions which are in this category, where we think we don't understand the underlying physics, therefore we can't answer the question. We try to convert them into a question where what kind of data would be required to answer that question, and that is how things progresses. And when we propose for new satellites, new observation, we try to push these questions to here and go ahead and say, okay, if we get this new data, we would be, and that is the reason for our ignorance right now. There's a third category, and I want to emphasize that there is a third category of, in general, astrophysics questions, which is neither of the two. It seems very difficult to get away by saying that you have not understood the underlying physics, and it's also difficult to say that you don't have sufficient data. Yet, you cannot answer the question. And that I would consider as a puzzle, because see a puzzle in one of your brain teasers and all, they've given you all the information, you are supposed to know what is happening out there, still you can't figure out what is happening, and that is what is called a puzzle. And one of the great things about anything is that what are the puzzles? For this thing, I'll give you 3 puzzles. Three puzzles means I don't know the answer to these questions. So I will start with the first one. Let's take a look at one of these black hole systems. There's a QPU here, and this QPU, which is higher, is twice this frequency, so it's called a harmonic. This harmonic. Now, what we find is the time lag as a function of energy is different for the harmonic and for the QPU. It's less. That means the high energy photons are coming after the low energy. The high energy photons are coming. The high energy photons are coming before the low energy ones. If the high energy photons are coming before the low energy ones, which we call as a soft lag, it means that this hot disk is varying first, and then the cold disk. So that is something which we can interpret. However, there are other observations where, for a quasi-periodic oscillation, which you see frequency, the time lag is opposite inside.
Hard lag one can understand because the hard X-ray is produced from the soft X-ray. The soft X-ray is there is a variability, the hard X-ray may come later.
No,
hard X-ray doesn't produce the soft X-ray.
No. You are looking at that point only when there is light travel time difference. See, the whole idea here is, let me go back to my image is far away. Is it? Oh, okay. If this varies, and then this will vary after some time because of the light travel time. But what we are talking about is some disturbance actually propagating from here to there, which would give you a hard lag. But if there is an oscillation here, and that propagates backwards forward, that will give you a soft lag in much longer time scales, like 1 second or not related to the light travel time effect.
That would be something like the sound travel?
Or sound or viscous travel times, or even if it is very fast, it can be the time taken for the heating of this disk from outside and the redistribution of the matter. Okay, let me get back to that one. This is a puzzle one. The time lag sign is different, which seems to, for the QPU at 3.5 and this QPU at 7 Hertz harmonic. Now, when we play musical instrument, we know that the fundamental and the harmonic comes from the same string. So they should have the same properties. But this is giving you opposite ones. How can something which has the same, like if you take an analogy of a string, how can the harmonic and the fundamental have different time lag situations? Perplexing? why shouldn't they have the same origin? Well, there are answers to this question. Harmonics are produced by non-linear processes. I mean, non-linearity is wonderful. When you want to escape from anything, you just say non-linear. So you have non-linearity. Once you have non-linearity, then we don't understand the underlying physics. We are safe. This is no longer a puzzle. But this seems like a slightly easy way to get out. And there are other people who said harmonic are the disk could be persisting, and it comes from a complicated. So people are trying to hide behind the fact that there could be some strong non-linear. But in general, this is getting a puzzle because we should know this. I mean, it is not something which we should know.
How do you know that it is a harmonic?
It's only
Only because it's twice?
because twice frequency, and also there is something called a bicoherence function, where we can look at a phase difference between that, and there also we have measurement that this is an harmonic. You know, bicoherence, I mean, I'll come back to that later. But right now it's twice the frequency. But we have ways, mathematical ways to share that whether something is actually a harmonic or two different frequencies. Just happens to be twice. There are differences we can figure out.
One quick question. How do you measure the phase lag between the, say, this QPO is coming first?
Between two energy bands.
Okay, the energy resolved.
This way. Sorry. This is energy. This is energy in the x-axis. So there is a time lag between 4 kV and 20 kV photons. And here also there is a time lag between 4 kV and 20 kV photons, but they have the opposite sign in the whole thing. So, but we don't understand this. But we can escape little bit. Okay. So now let me give you a puzzle number 2. This is a black hole system where we see a QPO frequency which is highly correlated with a spectral parameter. One spectral parameter which is called the photon index of the thing, highly correlated. So we see different QPO frequencies. So you look at it one time, look at it the next time, look at this time, we see different QPO and highly correlated. So this QPO seems to be of the same origin, it's just that it keeps changing its frequency. The origin of the, nature of this QPO seems to be identical, right? Same thing. However, its time lag changes at 2 Hz. And this we have seen now in 2 sources. That is the same phenomena. The time lag is flipping sign from positive to negative. That means below 2 Hz, the high energy photons come first, and the low energy, and after 2 Hz, the low energy photons come and the high energy photons. Why? There's of course another way. Complex geometry effects of a persisting corona, you can make it. People have done this and all. Both way feedback, which I'll talk about, I won't talk about right now, but there are ways to do this and all. But in general, this is a very messy thing and we don't really understand it. We're looking for people to explain this, to be short, in a whole thing. That is the challenge. But I'll finally come to a third puzzle. This is an absolute disaster. Disaster is a perspective, right? Sometimes disasters are wonderful things. Disaster is when you have to give up your hands and say, what do I do with this? This is a standard good black hole system, which I had shown you before, GRS 1915, very well-known black hole system. You observed it, and you see a QPO. Now this black, red, green, and blue are not at different times. They are at different energies. We clearly see evolution of the frequency with energy. You can plot it. The QPO frequency is changing with energy. Now, let me try to put forward why this is an absolute disaster. I'll make it small because I think I'm losing faith on this diagram because of this. Remember, I told you this is thermal compensation. Photons come from here, they scatter. How does a high energy photon go? It scatters 5-6 times and goes out, it forms a high energy photon. The more it scatters, it's higher the energy goes. That is what a photon comes in, if it scatters once, it will gain a little bit of energy. If it scatters twice, it gains a little bit more energy. So as it scatters more times, it goes out. So when you see a high energy photon, it has scattered from all over this place and come out. Yet, after it scatters out 10 times and comes out at some 20 kV, the frequency of the oscillation, the vibration of the system has changed. This photon has gone all around the place, so it should have, even if there was some frequency difference here and here, it should have picked up all. It should be incoherent. As you can see, there is very coherent thing that at high energy the photons are going in line. This is so disastrous that I'll give you another example of why do things like what I did. A year before AstroSat was launched, I remember reading a paper written by on using some older satellite RXT data, where they claimed that the QPO frequency changes with energy. I looked at it and chucked it. I said, they can't do this. This is wrong. It's not possible. It just doesn't happen this way anymore. And I forgot about it because the detection was weak, was very poor, and I didn't care about it. Then AstroSat came, and we're looking at it. And I remember this observation was one of the first observations we were looking at very carefully. And we looked at other QPO frequencies, and then I came to this. And one of the students showed me this. The frequency changing with energy. I said, see, we are setting up a new satellite, putting up this. I don't want to put up something as controversial as this. That the QPO frequency changing with energy, we are not sure of the systems. Let us the first in lakh species, so we send it off without. I said, there's no need to mention this. We have all our data. And then I conveniently forgot about it. Why did I conveniently forget? See, the bad things don't stick with you. They just remove it all. 6 months ago, 1 year ago, I get this paper from the Chinese HMXT papers. They claim that the QPO frequency changes with energy. And I said, oh, when I got back, and now I've looked at this, yes, I looked at it very carefully, it is changing with energy in the whole thing. How do you do it?
I mean, if your hard disk is optically thick,
Thin.
suppose it is
Thick.
optically thick,
Yes.
then the photon is not coming from far away, it's coming more locally.
Mm-hmm.
And the one which comes from the inner ring
Mm-hmm.
has higher Keplerian frequency as opposed to the one that is coming from the outer ring.
Hmm.
That will explain this behavior.
No,
No?
because this frequency is not in the Keplerian one.
Okay, I mean, that's very.
What?
He said it's possible.
Correct. Now, it is not, see, the point is, it's a good point. Let us assume, for example, there's one problem with this photon going around. Let us assume that low energy photons are coming from here and high energy photons are coming from there. Let's start. Difficult, but let's do it because against the spectrum. It is not that, these are not Keplerian frequencies. These are much lower than Keplerian frequencies. There is global oscillations. So you can have a global oscillations here, which has a different frequency than here. What that means is that within a fraction of 1-2 seconds, you will go completely out of phase. This part will completely go out of phase with the inner part, and there cannot be a global thing which is coming out of there. And we are observing this. We are observing this thing for a long time. Let's say 1,000 seconds. By then, matter has already swept through this thing many times. This is much longer than the viscous time scale. 1,000 seconds is a long time. It stays stable like this. Two frequency incoherent. If anybody seen how many, it's a terrible disaster thing. One possible solution. You put two QPOs. You put one QPO at 5.8 and one QPO at 7, and then don't change it with energy. Instead of having one quasi-periodic oscillation, you put two quasi-periodic oscillations very close by. So what you are doing is, you are saying that there is one quasi-periodic oscillation at low energies, there is one quasi-periodic oscillation at high energies, and the RMS of the high energy one is going up, the RMS of the lower one is going down. Possible, but to me this is contrived. I mean, you have to do something to match it up, but when we are in such trouble, what can you do? We can't do it. So what we need is people to look up. So I think the challenges which are being set up by this is what I would like to do. So I think I'll stop here, but I'll give you a summary. I'll give you a positive note summary first. The positive note summary is that, which I didn't talk about very globally, but I thought I'll do that. There are different ways we are trying to understand black hole systems. One which I didn't talk about is that full numerical simulations of Minotaur hydrodynamic simulations, which have not gone very far. Not that others have gone very far. Others is what I was saying, identifying observed frequencies with characteristic ones and trying to figure it out. I also talked about spectral components which are dragging this variabilities and all. So we need some kind of global comprehensive picture unifying these kind of schemes and going down there. But like the puzzles I show you, there are many questions which are left unanswered. And so I'll stop here, but because I do not know whether you have any more questions to ask. So I want to preempt by saying that the question which I don't know the answer to, so I will list them out here. First one, why do we have that truncation disk? Lots and lots of ideas, theories, nobody's convinced. Nobody knows why that thing is happening there. You know, one amazing thing is that you go and look at a black hole. Black hole is a black hole is a black hole. But black holes come in so many different shades and types. One wonders what is the reason for this diversity of things. We are not sure of that at all. What are the characteristic frequency correspond to? There's so many QPOs we see. We have identified a couple, and maybe by chance. How do we do it? There's something called jets. What they are, and that a lot of people here may have better evidence that what we know or don't know about jet. Then there's the fundamental question of why do you have an accretion disk at the first place? Because accretion disk to have, we need something called turbulence, and turbulence may not exist in such disks. What people propose is something called a Minotaur Mri instability has to happen for that thing to. Simulations have been ambidextrous in this, whether it really works or not. This is the reason why we cannot solve it from the first principle point of view. We look at it from observations. Will we ever understand GR and things like that? We don't know. And what about all these questions which we have, which we don't know the answer to, and we can't even hide from the fact that, we don't have the underlying theory and we don't have enough data. We have good data. We seem to know the underlying theory, but we still can't answer them. So this is the challenges which have been brought forward. So we will stop here and take any other questions which you may have. Yes. Yes, that now we have got an amazing capability for looking at optical variability in timescales of milliseconds, which was not possible earlier. I mean, not earlier, not possible about 5-10 years ago. What people are using that you need to use the full 10-meter telescopes. 10-meter class telescope because you need large collecting area, and from there you can measure the optical variability. And QPOs have been directed in optical, correlated with the ones in X-rays. And then there's a correction that where does the optical emission come from? Because the hint to that is probably connected to jet activity. That is, these accretion disks when they are oscillating, and then they're propagating on a jet, and that jet between the disk and the X-rays and the X-rays produced in disk, and optical produced in the jet are connected in this manner.
GMRT is observing it with AstroSat?
GMRT has observed it some.
And
but yes.
They have seen any variability with
No. GMRT will not be able to do this kind of variability. Okay. These are very rapid. We're talking milliseconds then.
Okay.
Questions?
Yes.
Or is it that the parameter space is still so unconstrained that you can't really say that?
No.
And one more question is when you say very many different kinds of black holes, you just mean many different kinds of accretion disks, right? Is that what you mean? Because they all come as just single black holes, curved black holes.
Okay. So my yes. Okay. Why is this not a verification of the reason why it is? You have to trust this estimation of this radius and this accretion rate. You have to trust the estimation of radius and the accretion rate, the spectral fitting of that. There are lots of, first is the theoretical modeling to fit the spectrum. The second is we have AstroSat calibration being done so correctly that you can say this with confidence. What about small changes in absorption column densities, things, variations, which can do that. So there are doubts there in the whole way. Otherwise, it is quite a strong theory. Yes.
I take it that variability of accretion rates have gone into the modeling of these systems, right? Are the puzzles and questions remain over and above that?
Oh yes.
It's
Okay. Wait. Modeling of a system, which you mean by numerical simulations?
no, for example, the radius changing with.
We don't know why the. No, first of all, we have one more problem here.
I mean, is the accretion rate assumed to be constant or variable with?
No, we don't know why it is a truncated radius. We don't know why the disk truncates out there.
Yeah, but if the rate is changing, then your position at which the truncation happens will keep changing, right?
Yes. And
has that gone into various
no,
models?
because we don't know why the disk truncates, we don't know how we should truncate with accretion rate. Did I answer the question?
Yeah.
The first problem is in a steady state disk.
Yes.
We want to see why, would there be a truncation like this? And this has been worked on for the last 30, 40 years. What you would require, let me go a little technical here, is that the standard accretion disk should become unstable. If it becomes unstable, then it will flip to another state, which is unstable. So this was proposed in 74, 75, long time ago, that certain conditions the disk will become unstable and then you flip it to the other possible state.
The accretion disk will become unstable even if it puffs up, becomes a thick accretion disk?
No, then it will become stable, right? Because when it's changing state,
Yeah.
I mean, the standard cold accretion disk, if it becomes unstable, it will change state and go into another. That was those ideas earlier. It was not borne out by theory, I mean by observation. Because the way this transition is supposed to occur, when radiation pressure is supposed to dominate, even when the system is supposed to be unstable, we see standard disks. We observe standard disks. So that was a problem there. Then there was this whole question about whether you can form this by evaporation of the material. And that's when I found out that evaporation is such a less understood physics in the whole process, and people try to, you put in by hand how much evaporation can take place from a disk or something, and that caused it. So people are working on this, but no real consensus on how to actually, so it is a phenomenological thing that we need a truncated disk, but we are not getting into theoretical ideas of how to do this, right? Sorry, which system? Which system exhibits power?
System talking about. Hello. And if you do PhD of that light curve, do you get the power law type noise? Or
you get I've shown power spectrums. You get something like this. This is a PhD.
Okay. This is PhD. Okay.
Versus frequency. I'll show you some more. That was a little strange one. This is a PhD. And the standard Cygnus X11 is the most prominent one, I think. Or this is classical PhD. No, not power law.
Okay,
You get complex shapes.
So we can't say from here, is there any disk jet connection or not?
No. Power laws are seen in AGNs and exhibit. That's because the data is very poor. I mean, we believe that systems are similar. So if you look at it very carefully, you should see something there. But you can approximate this with a broken thing or something like that. Then it becomes a power law for
Starting with the G-laxity detectors, and now that we have one, how overall the observation strategies have changed for this kind of sources?
No.
And in that context, I must say that you near the end you made a passing remark that some of those figures were generated in 1,000 seconds of data, and
longer.
I mean has been seen as low as 1,000 seconds as well. That is where the strength of the laxity instrument is.
Yes.
Detecting this kind of features in 1,000 seconds of data
Absolutely.
wasn't possible before, not in this energy band.
No,
And
not in high energy.
it may never come again.
It will never come again. That is true. In the whole thing. No, of course, the point is that the satellites are degrading. I mean, AstroSat is going down. The particular instrument which I'm talking about is the LaxPC instrument, which had 3 proportional counters, and now we are effectively left with 1 over there. So the effective area has gone down by a factor of 3, which means signal to noise has gone on by a factor of 10 in the whole thing for timing studies, because they go as constantly high with larger effective areas. So some of these signals, which, for example, this one I think is from very early times, 2016, all 3 PCUs. If you see this will have a factor of 3 or 4 less significance than that. So we have given up, at least I have given up in a long time, on doing things like kilohertz QPO's time lags. That I don't think is possible. We didn't get a very good observation in the first 3 go. We have not been able to do it again, I think.
Can you show that power density spectrum at different energy bands near the end of your talk? Yeah. On a lighter note, if you change the x-axis from frequency to KeV, one would believe this to be an X-ray spectrum with strong iron line.
Correct. And with a variable island. Variable island.
Okay. I mean, I think we are running out of time. Maybe 1 or 2 last questions. One last question, maybe. Okay, if there are no further questions, so let's thank Ranjeev again.
Thank you all.
Excellent talking.